All right, strengths of acids and bases. Now this is a bit confusing because some people confuse strengths with concentration, and that's not really the point. Or they might refer to the strength of an acid with regard to how corrosive it might be. So if any of you are fans of Breaking Bad, in the first season of Breaking Bad, Jesse had to dispose of a body, and he tried to dispose of that body by putting it in a bathtub and filling the bathtub full of hydrofluoric acid.
I'm sorry, what were you asking me? Oh, yes. That stupid plastic container I asked you to buy. You see, hydrofluoric acid won't eat through plastic. It will, however, dissolve metal, rock, glass, ceramic. So there's that.
Hydrofluoric acid, if you remember HF. It's actually used to etch glass, and the reaction that they, in the scene, obviously it's Hollywood, where they exaggerated tremendously on this. And the acid, well anyway, it doesn't really behave that way, but HF does dissolve glass, and so it has to be kept in a plastic container. But nevertheless, this is a weak acid. So it's very corrosive, but it is a weak acid. All right, so HF is a weak acid. So do not confuse strength with the corrosive nature or concentration. For example, you can have, say, a 12 molar solution of hydrofluoric acid. This is not a strong acid. HF is a weak acid, but it's a concentrated weak acid. In addition, you could have, I don't know, 0.1 molar HCl. Well, 0.1 molar, this is a low concentration, so it's a dilute, strong acid. So hydrochloric acid is a strong acid. The term strong and weak refer to the type of acid, not to the concentration. So, all right, so what do we mean by strong and weak? All right, so it says here, strong acids completely ionize, or if you wish, ionize 100% in solution. HCl, as I said, is a strong acid. If you dissolve hydrogen chloride gas into water, 100% of it will dissociate. So 100%, if you wish, of these hydrogen ions, right, get donated to the water. So all you have left in solution is hydronium ions and chloride ions. In other words, there is no HCl left swimming around in solution. No HCl aqueous, right? We don't have any hydrogen chloride molecules in solution. It all reacts, so 100%. Weak acids, now you might hear different thresholds for this, but I'm going to say, all right, a strong is 100%, anything less than that is weak. So anything less than 100% is weak, and just make it easy that way. Carbonic acid is a weak acid, and one of the other things you'll notice here, this is a one-way arrow, so it's an irreversible reaction. In other words, this going backwards, water donating a hydrogen ion to chlorine to get HCl back, this does not happen. But it does work the other way. So weak acids have an equilibrium arrow. Right. So carbonic acid will donate a hydrogen ion to water. H2O becomes H3O plus, the hydronium ion. But the hydronium ion could also donate a hydrogen ion to the bicarbonate ion. This is the bicarbonate ion, or the hydrogen carbonate ion. And when it does that, H3O becomes H2O. We're donating a hydrogen ion here, right? Hydrogen ions are getting donated. We donate a hydrogen ion to HCO3, it becomes H2CO3, so going backwards. Now these arrows are not of equal length. Okay? And we'll get to that in a little bit, but it's important to point out now. All right, so weak acids do not dissociate 100%. So dissociate only slightly. It says here slightly. So I'll say here less than 100%. So H2CO3, all right, this is what happens. Well, we're gonna draw, say, a beaker here and put some water in it. And we're going to take a tube, and I won't talk about how this happens, how you can do this, but there's certain reactions that generate carbon dioxide gas. So we're bubbling carbon dioxide gas into water. Okay, what happens there? Carbon dioxide is a gas. We dissolve it in water, and we get this combination reaction, H2CO3. All right, so now we have H2CO3 in this as the carbon dioxide reacts with the water. So this is now carbonic acid in solution. Some of this will also react with the water, given this reaction up here. So what we have actually in this, as we're dissolving carbon dioxide in water, we have not only carbon dioxide molecules, right? We have the carbonic acid molecules, H2CO3. Only some of course, we have water molecules. Only some of this reacts, though not all of the H2CO3 reacts, unlike the HCl where all of it reacted, so there was no HCl molecules. Here we do have some H2CO3 molecules, but we also have the HCO3 ion, the bicarbonate ion, as well as hydronium ions. So you have a lot more things swimming around in solution here. You've got the carbon dioxide gas, the carbonic acid, its conjugate base, and the hydronium ion. All three of these species, this guy, and this guy, all three of them swimming around in solution. But it says here only slightly, and that's what this longer arrow is trying to indicate. And we'll talk more about that on the next few slides. All right, so a strong acid dissociates 100%. So initially you have HA, and this could be, could be like the HCl that we talked about, but we used HCl before, so let's use here HBr. It dissolves in water. You get the hydronium ion and the conjugate base bromide ion, and there is no HBr left in swimming around in solution. It's all reacted. That's a strong acid. Right? It has nothing to do with the concentration. Weak acids, not quite. I mentioned before, hydrofluoric acid is a weak acid, so we have HF. It's a gas. You dissolve it in water. Most of it is actually going to stay as the hydrogen fluoride molecule swimming around in solution. A little bit of it will react with the water, right? So a little bit of it will react with the water to give you the hydronium ion and the fluoride ion. But most of it, dissolves in the water without reacting with the water. So it stays as it was before, but now it's simply this molecule in solution. And again, they're showing that this longer arrow means that most of the acid is not ionized. Most of it stays as HA, or specifically here with hydrofluoric acid, HF. That's what this longer arrow means. We say this longer arrow favors reactants. The shorter arrow means we have fewer of the products. Right? Fewer products, shorter arrow. More reactants, favors the reactants. The longer arrow going towards the reactants. Again, just a kind of a pictorial view here. HCl is a strong acid. Right? So we have chloride ion and all these hydronium ions. So notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9 chloride ions. So these are all chloride ions, and there's 9 of them. So there ought to be 9 hydronium ions. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 hydronium ions. So they all reacted, all 9. You don't see any there. In other words, there's no HCl molecules swimming around in this bottle of 1 molar HCl. Acetic acid, right? Acetic acid here now is a weak acid. Remember, this is the only hydrogen that's present, so it's monoprotic. It's a weak acid. So here we see an acetate ion, and here we see 1 hydronium ion, and that's it. Most of them are unionized, right? This guy, this guy, this guy, these all have the hydrogen ion present. They do not dissociate. So we have CH3COOH plus water. Actually, do it this way. Favors reactants. We get the hydronium ion and CH3COO minus, the conjugate base of acetic acid, the acetate ion. So what we had, what if there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So there's 9 of these now, and that just gives and just 1 hydronium ion and 1 acetate ion. So the equilibrium favors reactants. This is a weak acid. Most of it stays unionized. I use this term unionized. Unionized. Not unionized, but unionized. Right? Versus the ionized. Alright, so I gave you a list earlier of the acids and bases that I wanted you to know, and I wanted you to be able to tell me if they were monoprotic or diprotic and whatnot. Now you also need to tell me if they're strong or weak. Now, it turns out that there are many, many, many weak acids. There's just a few strong acids, and actually I'm only going to ask you to know 5 of the 6 here. I mentioned before you don't need to worry about perchloric, but sulfuric acid, nitric acid, and then the halo acids. So if you remember the halo acids, we had hydrofluoric, hydrochloric, hydrobromic, hydroiodic. These 3 are strong, and I won't get into why this is. Take a higher level chemistry course like second semester college chemistry, natural science 212. We learn more about this, but this guy is weak. So I don't ask you to memorize the weak acids. I just want you to know 1, 2, 3, 4, 5 of the strong acids. Any other acid by default, then any other acid by default is weak. So don't try memorizing the weak acids, memorize these strong acids. If it's not on your list of strong, it must be weak. There's many, many, many weak acids. Don't worry about memorizing these. Strong bases. We have strong bases and weak bases. So strong bases are formed from group 1A and 2A. Let me just remind you, 1A is referred to as alkali metals. Remember way back when we talked about the names of some of these groups. 2A, alkaline earth metals. The term alkali or alkaline is another way of saying base. So these are the 2 guys that form bases, and they're strong bases. So they're solids. When they dissolve in water, they completely ionize. So it's 100% ionization. And so really for the most part, group 1A and 2A, those are your strong bases. There's really only one weak base that I ask you to know. Only weak base that I'm going to ask you to know is, it says weak base. Let's get rid of that. The only weak base that I ask you to know is ammonia, NH3, right? Or if you wish, again, this is a misnomer, ammonium hydroxide. Most other weak bases, well, let me put it this way. Most other weak bases are either derivatives of ammonia, or if we go back to the weak acids, these are all weak acids. Right? Their conjugate base, so here's the weak acid, H3O, the conjugate base. These are conjugate bases. These are conjugate bases. These are the weak acids. It says weak acids make up most of the acids. They have strong conjugate bases, and that's actually that's not true at all. These weak acids also have weak conjugate bases. I have to change that. So anyway, water is a weak acid. H3O plus is a weak acid. Its conjugate base, water, is also a weak base. So these are also weak bases. Okay, so weak acids, if you just remove a hydrogen, right? H3PO4 becomes H2PO4. This is a base. It's also a weak base. It's not strong. It's a weak base. So weak bases are simply the conjugate base of weak acids. Let me write that down. Okay. I said the one weak base that I really want you to know is ammonia, but the other thing you can say here is conjugate base of a weak acid is a weak base. Now I'm only going to touch on this. You see some equations, some mathematical equations here. I don't want to dwell on this too much, but remember, let's think of it this way. We have here the percent dissociation. Right? If it's 100% dissociation, we say it's strong. Right? Anything less than that is weak. So it could be 99%, or it could be 90, or it could be 50, or 40, or 20, or 2, or 1% dissociated. It doesn't matter what percentage it is, so long as it's not 100. These are all weak. Okay? But they're all various, if you wish, different strengths of weakness. Right? You can have only one winner, one champion in a sports competition, but you have say a race or whatever. You've got only one first place winner, but then a bunch of other losers. So you've got the first loser, the second loser, the third loser, and so forth. So how do you rank these different weak acids or weak bases? See, these are all weak, but 90% is still stronger than 40%. Right? Someone who comes in third place is much faster than someone who comes in 10th place, for example. So they're all weak, but yet have different strengths. And I'll put strengths in quotation marks because I don't want you to think of this as saying that they're strong. I'm just saying they have different degrees of weakness, maybe. All right. So the way we do this is with something called an equilibrium expression. The expression is a mathematical structure here. So this expression is this business here. This KEQ is the equilibrium constant. So call it here the equilibrium constant. Equilibrium constant. Constant with the K, right? So K for constant, EQ for equilibrium. This constant is a number, and we'll see those numbers in a moment. It's calculated by looking at the various concentrations of these guys. Now, if you'll notice, this is a weak acid. I'm using blue, but nevertheless, it's a weak acid. Here's its conjugate base. And what you notice is they basically took the products. Here you got products. Here are reactants. And they just took a ratio of them. So we've got products over reactants. And why do we do it this way? Why is it not reactants over products? Again, you'd have to take Chem 212 with me if you wanted to figure that out. But for now, just recognize that the equilibrium constant is a ratio of products over reactants. So this arrow here says it's longer, so it's favoring the So it's favoring the reactants. That means we have more reactants than we do products. So what does it mean when you've got a ratio where you've got a lot of reactants, so a big concentration of reactants, and a smaller, I'll just make it a little smaller, a little bit of products? Well, this is going to be a fraction. It's going to be something less than 1. This ratio is constant. It doesn't change. And so we don't express acids and bases with regard to percent dissociation, because it turns out percent dissociation is not constant. It depends upon the concentration. But here, the ratio of these concentrations is constant. And so we plug these concentrations in, do the math, we get an equilibrium constant. That's a KEQ. And for acids, we use the Ka, A for acid. And for bases, it would be the Kb, B for base. So this would be for a weak base. I won't get into the details here, but what they've done is they've multiplied each side of this equation. Maybe we can do this here. Let me go ahead and erase a little bit of this. So yeah, it's a ratio of reactants over products. And what they did then is essentially just multiplied each side by the concentration of water. Right, so this Ka here, this is the concentration of pure water times the KEQ, and now we call it the Ka. So they just got rid of the H2O term here. That's all. So don't make a big difference, a big deal about it. Basically, it's still ratio of products over reactants. The equilibrium, so the equilibrium position is given by this Ka. When you have strong acids, remember equilibrium position favors products or it's towards products. So say favors products. So in our reaction here, right, it favors products. So just put a tiny little arrow here. So for strong acids, really there is no back reaction, but a very equilibrium arrow, if you were to draw one, would favor products, a long arrow towards the products. What this means is, because again the Ka is a ratio of products over reactants, we've got a lot of products, very little reactants, and so it's a large number over a small number. It's going to be large. For weak acids, it's just the reverse, right? So here it favors reactants. Right? So we have, here's our reactants. Very small arrow going towards products. We've got a lot of reactants, very little products, and so the ratio now again, this KEQ or the Ka is products over reactants. We've got very little products, right? Arrows going towards reactants. We've got a lot of reactants, so a large number here on the bottom, small number on top. What do we mean by large and small? Well, it might be 1 over like 10,000 or something. Oh, that's too many. Put it this way. Okay, 1 over 10,000 or something like that. Okay, that would be a very typical kind of Ka you would see. What is this? This would be 10 to the negative 1, 2, 3, 4, 10 to the negative 4. Okay, that'd be a very typical number you'd see for the Ka of a weak acid. So very little products, a lot of reactants. And it says here the weak acid conjugate base. No, this is also weak. Conjugate base of a strong acid, yeah, it is weak. So this is, I'm not going to get into the details here, but that's true. These are also weak. Don't have to know any of these numbers, but I just wanted to point out that these are also, they're small fractions. Phosphoric acid, 7.5 times 10 to the negative 3, what is that? 0.0075, right? Small number. something like acetic acid, 1.8 times 10 negative fifth, 0.1234518. So very, very small numbers. The smaller the number, the weaker the acid, right? Smaller Ka equals the weaker acid. So the acid strength is decreasing as you go down this table, right? The larger the Ka, the stronger the acid. And again, same thing goes for bases. These are Kb's now, not Kas. These are Kas. Kb's, the smaller the Kb, the weaker the base. The larger the Kb, the stronger the base. Don't memorize any of these numbers. You don't even have to memorize that these are all weak acids, because none of these are on your list of strong acids. Remember, if they're not on the list of strong acids, they're weak. The next lecture then we'll talk about the ionization of water. And just so you know, we talked about water. Water is a weak acid. It's also a weak base. Water is amphoteric. Right. So water can ionize to give you hydrogen ions and hydroxide ions. That would be in the Arrhenius sense. So it ionizes and produces hydrogen ions in water, an Arrhenius acid. It also produces hydroxide ions in water, an Arrhenius base. So it's both. It's amphoteric. And that's kind of like what they're showing you here, except they're giving you the hydronium ion. That'll be the next lecture.